So hello everyone. My name is Kaustubh. I am a junior at Amador Valley High School.
My name is Tarun Mahesh, and I'm a junior at Hillsborough High School.
And my name is Aryav Das. I am a sophomore at MSJ, Mission San Jose. There are also many other members of our group who sadly couldn't make it today, but their names are included in the slideshow.
Okay, I believe I is the presentation shared?
Yes, we can see it.
Okay, thank you. So yeah, thank you, Dr. McMahon, for that introduction. Like he said, we are using autonomous drones for terrain mapping and route creation and optimization to enhance search and rescue operations. So basically, in a nutshell, what we're kind of doing is using autonomous drones to kind of just take images of terrain, kind of map it out, take pictures, images, models of whatever the terrain is of some place that's been hit by a natural disaster or something. And it uses that to find the most optimized route for first responders to get to wherever they need to go. So, kind of like I touched upon, the problem is that it's very hard for these first responders to find accurate real-time information for the terrain that they're looking at. So, say something like an earthquake hits, of course, things like Google Maps, which are very good at optimizing routes, are not going to be updated that instant with the new terrain that's been hit by an earthquake or a flood or a landslide. So these things change the terrain extremely quickly and are it's very important to get that information as soon as possible so that these first responders can get to wherever they need to go and rescue whoever needs to be rescued, of course. And the current way that, or one of the ways that they do it right now is that they do grid searches, which, of course, like the name implies, is just searching by grids or by sectors of a grid to kind of map out the whole terrain before they start sending people out. But of course, the problem with that is that it is very slow and time consuming in context of a natural disaster. So you really don't want to waste time just doing a grid search while there are people who need immediate assistance. So yeah, that's kind of a pretty big problem with first responders and terrain mapping after a disaster.
So we found some related works that have to do with what we're talking about in our paper. First, we found a paper that talks about 2D laser range finders with mobile robots for terrain mapping. And this paper focuses on using a drone to recognize characteristics of different terrains. For example, finding the difference using a LiDAR image of between concrete and grass. And we'll probably be using technology like this because traveling on concrete is different than traveling on grass. And similar to what we're planning, this paper talks about a robot that's completely autonomous. And secondly, we found a paper about UAVs and GPS onboard registration. Similar to our paper, this uses medium accuracy topological mapping, which means that it'll use a LiDAR camera to make a 3D map. And it uses photogrammetry, which means that it'll use images of different angles to form a 3D model.
Now on to other solutions. For a long time, EMS have been using many of the previous mentioned solutions alongside others such as helicopters and larger drones. As Kaustubh mentions, grid searches can firstly be very time consuming as most of them are by foot and use a lot of resources as many search parties are required to cover this area. Additionally, these helicopters, drones, and grid searches all use previous GPS data, which can be outdated and potentially dangerous due to the severe changes in environment after the natural disaster or whatever effect. So now on to our solution. Our solution is to use a small, cheap, and lightweight, easy to manufacture drone. In this case, we're using the Clover Quadcopter 4.2 to cover large areas of ground between point A, point B, and map it out, and thus create a 3D map that can help all of these EMS services quickly navigate from point A to point B, potentially saving lives. So how we plan to go about this? Our methods, we are using a mostly 3D printed Clover quadcopter. The frame and the outer shell of it is all 3D printed. The only additional parts are a Raspberry Pi, motors, and other controllers. This makes it both cheap and easy to get anywhere on the go. By using a combination of LiDAR sensors, GPS, and cameras, we plan to integrate YOLO with CNN and create an object detection model that can detect and differentiate between different types of terrain. As Tarun earlier mentioned, differentiating between terrain can greatly help us identifying the safest route from point A to point B. Finally, as mentioned below, you can use simultaneous location and mapping, also known as SLAM, to help create this 3D terrain. Okay, and now on to you, Kaustubh.
Okay, so we all know that in science, the best way, or one of the best ways to visualize things and kind of make things a lot easier to see is using models. Now, this model can be a chart, a graph, maybe some physical reconstruction of something, but the model that we elected to use was CAD, which, for those of you who don't know, means computer assisted design. And we specifically CADed in Fusion 360, which is a 3D modeling software. And using this software, we were able to kind of put together the drone in a virtual world, and we're able to kind of easily visualize where things go, where we can put things in the future. And it's a really efficient tool to see what we can do with the drone. And like I said, it'll be used to determine the location of future additions of components. So one example of this would be the LiDAR sensor. And the LiDAR sensor hasn't been added onto the drone yet, but using the model, we can figure out exact placement of maybe using weight distribution calculations or whatever. We can find out exactly where we want to put the LiDAR. And kind of like I just touched upon, we can do a lot of theoretical calculations with CAD analysis tools as a means to either double check what we have previously done or kind of to lay a foundation of the sort of bounds that we can work in. So I would like to show the CAD model actually really quickly, just so you guys can get a visualization of what that looks like. So yeah, so here's the Fusion 360 CAD model. Um, it's a really efficient and nice tool to kind of visualize everything when we're maybe not in the lab or when we want to do something like instantly. So just a couple examples that we have the Raspberry Pi right here. We have our camera right here, and then our motors and propellers on the four edges. And CAD is just a very effective and convenient tool that we like to use. So let me share the presentation again. Okay.
Okay, so now we'll talk about our end goals, which are as follows. First, we want to have a fast overall time from when the drone launches, the data processing to the route output. So overall, no time is wasted and we reach 100% efficiency. And the speed is important because if this drone is going to be used for search and rescue missions, getting fast results is essential. So multiple trials will be crucial for tuning parameters and making sure that this model is as fast as possible. Furthermore, the reliability of our drone is important. We want our drone to be sturdy when flying and our data processing and route output to be reliable so that it won't create weird routes and lead responders astray. So we want to make sure that the drone is able to be reliable amongst many different terrains. So once again, multiple instances of trial and error will be necessary. Finally, a cost-efficient drone is important because we want to have a system which has the lowest financial burden possible on us researchers as well as the ASDRP team and on the emergency responders that we hope one day will use our system. So for the possible practical applications at play, it is necessary for a cheap drone with great quality. So here are our acknowledgements. We would first like to thank ASDRP for providing us with this opportunity to research this area. We would like to thank Dr. McMahon for showing us how research is done and the steps that we need to take. We would like to thank Mr. Downing for helping us procure the parts necessary and providing us with the valuable insight in the hardware and software aspects of our research. And we would like to thank our fellow researchers, including Arya Iyer, Arsh Mithal, Rashil Dalip, and Nikhil Sinha for contributing heavily to our research.
Thank you all so much for listening. Hopefully that was interesting. And now we'll open it up to you guys if you have any questions for us.